Hello and welcome to the VIP Cup 2020 finals. I am Said from BUET Synapticans. We are here to present our work on this year's challenge on real-time vehicle detection and tracking at junctions using a fisheye camera. Before beginning, I would first like to introduce our team members. We have Dr. Tawfiq Hassan Sar as the supervisor and as our mentor, Uday Kamal. The rest of the team members are Partho Ghosh, Naib Rashid, Hasan Habib Akash, Swapnil Shaha, Mohammad Abrar Ishtiaq, and myself, Mir Said Mohammed. Now, let's take a look into the contents of this presentation. First, we will be discussing the task overview. Then comes the dataset challenges, vehicle detection framework, detection evaluation and results, vehicle tracking workflow, and finally, we will have a discussion on the entire work. The dataset provided for our task included traffic images taken with a fisheye camera. The first task is the real-time detection of vehicles present in the frame. The second task is to track the vehicles that were detected in the previous step and obtain their trajectory. Let's now take a look at the challenges the dataset poses. First of all, because of the fisheye camera, all the dataset images are spherically distorted. A direct impact of the spherical distortion is that vehicle sizes vary greatly depending on its location in the frame. Due to the overhead positioning of the camera, vehicles in the frame have a wide range of orientations. A common challenge in vehicle detection is that some of the objects might be partially occluded, which is difficult to handle for a detector. Sometimes the same object might be marked as two separate ones. The dataset contains two types of images, day and night data. Daytime images are generally bright. The night data has lower brightness and its unique feature is the car headlights. This causes the whole dataset to have two separate distributions. Now, let's take a look at the previous works in this field. There has been some work on handling fisheye images and some other methods suited to the vehicle detection task. However, to our knowledge, there has not been any work on vehicle detection and tracking from fisheye images. That's all from me. Now, I'd like to ask Parthok to have a discussion on the framework that we used for the vehicle detection task.
Thanks, Said, for giving me the floor. In this flowchart, we can see the whole architecture of our detection model. Here, we have used a detector to detect whether the input frame is for day or night. Then, we use two different networks to detect the vehicles and ensemble their prediction to localize all the vehicles in the input frame. To detect an input frame, whether that is for day or night, we first try to look at the difference of their pixel values. But from the plot, we can see that their distribution overlaps. Therefore, we used a SqueezeNet network to detect the frame as day or night. In this slide, we could see the whole architecture of SqueezeNet block by block. For paradigm 1, we used an anchor-free detector named UniverseNet. The detector uses raised-to-net 50 feature extractor as the backbone. The feature returned by the backbone are then used by the feature pyramid network, and after that the feature stack goes to the ACPC block. In the ACPC, a special type of 3D convolution is used named scale equalizing pyramid convolution, which performs better on small object detection tasks. The feature returned by ACPC is used to return the classification prediction and the bounding box predictions. For paradigm 2, we use a variant of YOLO object detection model which uses customized CSPNet feature extractor as backbone. The features extracted from the backbone are then passed on the neck, which is a path aggregation network. This part mixes and combines the features from the previous stage and passes it onto the prediction layer. In the ensemble scheme, we first generated bounding box prediction from both models, and then according to the model's performance, we used a different confidence threshold for both of the models to reduce unnecessary detections. After that, all the predicted bounding boxes were concatenated. Then it passed through NMS to remove overlapping prediction, which ultimately gave a better performance. In the training scheme, we used all the training data of both day and night for training, and for validation we used the testing data. At first, we trained our day-night detector. The hyperparameter used in the training is shown here. Then we trained UniverseNet, where we first fine-tuned the model on the whole training data on Cocoa pretend weight using the default settings. Then we further fine-tuned the model on the day and night data independently. At this stage, we used some basic augmentation. After that, the YOLO V5 model was trained on Cocoa pretend weight for the combined data. In this stage, we used some data augmentation mentioned here. Then we further fine-tuned the model on the day and night data independently. This is all from me. Now I would like to ask Naib to carry on the discussion on detection, evaluation and results section.
Thank you, Bartol. So we conducted different experiments on the UniverseNet model, and this plot here shows the detailed results. The mark points are the best weight for the day and night data which are selected for our final submission. We see a similar plot here for the YOLO V5 model, and the mark points indicate the best weight selected for day and night data. We also conducted an experiment to see the effectiveness of our ensemble scheme, and it can be clearly seen in this bar plot that the ensemble of two paradigms achieve a greater MAP score than the individual paradigm. This basically concludes our vehicle detection framework. Now we move on to our vehicle tracking methodology. At first, the SORT algorithm was used. The algorithm takes vehicle detection from the detection network and updates the history of tracked vehicles with the help of a Kalman filter. Each new detection is matched with the recorded tracks using the Hungarian algorithm, and then dead tracks are removed, new tracks added, and running tracks updated. Initially, we ran the SORT algorithm on the dataset. Then we tuned the parameters for occlusion handling. After that, the exponential mean was used for a smooth trajectory. In the following video, we can see the improvement by applying these modifications. By this, we conclude our discussion on our vehicle tracking workflow. After the published result on stage 2, we investigated our model performance to understand why it was generating high amounts of FP. As a result, we saw that a lot of moving small cars were predicted by our model, which was not part of the ground truth. This caused a reduced MAP score for our framework. That is all from us. Thank you everyone for your patience. Please feel free to ask any question.